Okay, let's dive right into this. Welcome back to The Explainer. Today, we're taking a close look at the foundational principles behind electric drive systems. Now, I want you to shift how you typically think about these systems for a second. Don't just picture a basic machine. I want you to think of an electric drive system as a highly specialized, elite team of components. And just like building a championship sports team, you can't just throw a bunch of random star players onto the field and expect them to win the game, right? Our overarching goal today is to really unpack the meticulous process of selecting the absolute perfect team of components. We're talking motors, power sources, converters, and controllers, so they work together in absolute harmony.
So, here's our roadmap for today's explainer. First, an intro to drive selection. Second, choosing the perfect motor. Third, mastering speed and torque. Fourth, the role of converters. And finally, advanced converter criteria. Let's get right into it.
Section 1. Intro to drive selection, building the perfect team.
An electric drive system is literally just like a chain. It is absolutely only as strong as its weakest link. Seriously, you could go out and buy the most expensive, most powerful motor on the planet, but if you pair it with a power converter that just can't handle the electrical current, the entire system goes down. To build it right, we're grounding our explainer today directly in the source material, specifically Chapter 2, Selection of Electric Drive Systems. This gives us a rigorous fundamental engineering framework to understand exactly what the pros are looking for when they build these setups from the ground up.
All right, Section 2. Choosing the perfect motor, the muscle of the system.
Okay, so if the electric drive is our team, the motor is undoubtedly the muscle. And just like an athlete, different muscles are built for completely different types of work. I mean, a marathon runner's muscles look and function totally differently than a power lifter's, right? Now, what's really interesting about the criteria we're looking at is that when evaluating this mechanical muscle, engineers look at 4 primary things. They look at rated speed. So is this a high-speed or low-speed application? They look at rated torque. Do we need a ton of twisting force or just a little? They calculate the overall power required. And finally, they look at power density. These 4 pillars pretty much dictate the entire game of motor selection.
I actually want to pause on that last point for a second, because it's an absolutely crucial concept in modern engineering. Power density is defined as the power-to-volume ratio of an electric motor. So why does this matter so much? Well, because we aren't just looking at the raw, absolute power output of a machine. We have to consider exactly how much of that power we can pack into a specific physical footprint. If you're designing an electric vehicle or, say, a robotic arm, you don't exactly have unlimited space, do you? You need a motor that punches way above its weight class physically.
And all of this is tied together by a really elegant fundamental mathematical relationship: power equals torque multiplied by angular velocity, or P equals T times omega. This one little equation literally drives almost all of our engineering choices here. Think about it. If you have a fixed amount of power, you have an inverse relationship between your torque and your speed. If you want more rotational speed, you're going to have to sacrifice torque. If you need massive twisting force, meaning torque, well, you're probably going to have to sacrifice some speed. It's always a trade-off.
Moving on to Section 3. Mastering speed and torque, a balancing act.
Because of that mathematical balancing act we just talked about, you really have to clearly define what the mechanical load actually demands of your system before you can even think about picking the motor. Let's contrast these 2 applications directly. On one side, we have high-speed motors. Now, these are absolutely essential for operations that require incredibly fast linear or rotational motion. Think of high-speed cooling fans or super precise machine tools. Then on the flip side, we have high-torque motors. These guys are built for the heavy lifting. They handle heavier, high-energy loads. Imagine an elevator, a massive crane, or a train locomotive pulling thousands of tons from a dead stop. You just can't pick one standard motor for every type of job. The physics absolutely will not let you.
But hey, it's not just about picking a single static number and calling it a day. A motor's relationship with torque is dynamic, which brings us to motor torque profiles. The source material outlines several key dynamic requirements we have to hit. We have to look at the overall torque speed profile for sure, but we also have to consider starting torque, like how much force is needed literally just to break inertia and get the thing moving. We also need to look at peak torque capability. That's the motor's ability to withstand sudden, short-duration bursts of resistance. And finally, acceleration. Your motor has to survive and thrive during these crazy dynamic changes, not just when it's cruising along at a steady state.
Let's look at a really specific matchmaking example straight out of the text. Say your application demands a strictly constant speed, regardless of minor fluctuations in the load. Well, a synchronous motor is your absolute go-to choice. Its torque speed profile is just perfectly suited for this. If you were to try and choose a different type of motor for a constant speed job, you'd end up having to build these really complex control systems just to artificially compensate for the speed changes every single time the load shifted. It'd be a nightmare.
Here's another incredibly practical application from our source. What if your main problem is getting a massive load moving from a dead stop? Where high starting torque is the absolute top priority, the text points us straight to DC series motors. They just excel at providing that massive initial starting push. But, and this is a huge but, here is a crucial environmental consideration you must factor in. You absolutely have to avoid DC motors in hazardous or highly flammable areas. Why? Because of the very real risk of sparking from their brushes. So matchmaking really means looking at the operating environment, not just the raw physics.
All right, so we've carefully analyzed our load, and we've got our perfect motor. Our mechanical muscle is completely ready to go. But that leads us to a pretty pivotal question. How do we actually feed it the exact right kind of electrical power? Motors can be incredibly picky eaters, you guys. We can't just plug them straight into the wall and hope for the best.
Which brings us to Section 4, the role of converters, the system's translators.
You really want to think of power converters as the critical translators of the system. The power grid might speak alternating current, or AC, but your specific motor might only speak direct current, or DC. So depending on your power source and your drive, you have some very distinct configuration paths. For instance, an AC source feeding a DC drive requires an AC to DC converter. Pretty straightforward. But if your source is already DC, you might still need a DC to DC converter just to step the voltage up or down. And for AC drives, it gets even more complex. You might have to take an AC source, convert it to DC, and then flip it back to AC to get a highly variable, perfectly controlled output. It's this whole complex translation process required to meet the motor's exact dietary needs.
Section 5. Advanced Converter Criteria, the fine print. So picking the actual configuration is really just step one. Now we have to read the fine print. Our source lists several secondary characteristics that literally make or break a converter's viability in the real world. First, obviously, is its absolute ability to handle the required maximum currents and voltages without, melting down. Second is efficiency, like how much power are we losing as heat during this whole translation process. Third are the dV dt and di dt limits, and finally, noise levels. And just to be clear, that means both physical acoustic noise as well as electrical interference that gets injected back into the system.
Let's actually demystify that third point right now, because it's a bit of technical jargon, but it's absolutely vital. dV/dt and di/dt simply refer to the system's ability to survive rapid electrical spikes. The D just stands for delta, or change. So we're talking about the rate of change of voltage over time and the rate of change of current over time. In the real world, power isn't always perfectly smooth. A converter has to be robust enough to withstand incredibly sudden, high-speed surges or drops in power without failing. If its dV/dt limit is too low, one quick spike will literally fry the components.
So as you can see, building an electric drive system is this intricate, beautiful dance of compatibility. You match the load's speed and torque profile to the perfect motor. You map the power grid's output through a highly specific converter to feed that motor perfectly. And finally, you orchestrate the whole shebang with a controller. Selecting the brain of the operation means carefully evaluating its I/O units, the peripherals, memory capacity, computational speed, and of course, cost. In electric drives, a perfectly engineered component is completely useless if it doesn't match the rest of the system. Every single piece relies on the others. So armed with this fundamental understanding of selection criteria, what kind of system are you going to build?